So, hello everyone. Myself Kunal, and I am your mathematics tutor. And we are actually doing definite integration. And today is our eighth lecture on definite integration. So let me recap. अभी तक हमने क्या क्या कर ली. So we actually हमने सारे प्रॉपर्टी देख रखे हैं. Like Wally's formula, odd even, King's rule, Queen's rule, and all. And जो भी fourth property थी, like we are integrating from 0 a to or 0 to nt for where t is the period of the function fx. So we can write it into a 0 to t and t fx. We इसमें हमने चार पांच इसके पार्ट पढ़ रखे हैं, right? So today we are gonna learn something new, which is known as so let us start our today's lecture, and today we are going to learn something new, which is also known as a derivative of antiderivatives. So let me write the topic's name here. It is like derivatives of antiderivative. We all know that the antiderivative is nothing but integration. So we have to learn today the differentiation of integration, right? अभी तक हमने क्या पढ़ा? आपने पढ़ा होगा डिफरेंशिएशन, हमने पढ़ लिया इंटीग्रेशन, एंड नाउ टुडे वी गोना लर्न differentiation of integration, right? And it is also known as Newton Leibniz formula, right? It is also known as Newton Leibniz formula. So we are going to learn today derivative of antiderivative. Okay, so let me start that. So let me write its formula first. So we can connect to it. So we can connect to its name as well. So why it's called derivative of antiderivative. So let me write here the formula. It is something look like d by dx, and we are integrating from phi of x to something g of x. There is ft dt. So this is actually equal to f of gx and dot g dash of x, differentiation of g x, and then f of phi x, and then differentiation of phi x. So this is our actually Newton Leibniz formula. So actually we are going to prove it as well. So first try to understand it, how it is connected to its name, and then we learn how to implement it problem as well. Okay, so this is our derivative. So we know that the d by dx is derivative, and this integral part is also known as antiderivative. So according to our name, it is the derivative of antiderivative, right? So we are differentiating which actually something integrate first, and then we differentiate to the integration. What I'm doing here, I this is my integrand. So first I integrate this function with the elementary element something t, and then what I'm doing, whatever I get as a product, then we uh, differentiate this whole integral or the antiderivative with respect to x. So what we get? We get a composite function like f of gx and the differentiation of gx minus f of phi x into differentiation of phi x. So let me recall you यहाँ पे हो क्या रही है. So इसको जरा सा डेप्थ में अगर देखते हैं तो व्हाट आई एम डूइंग हियर, आई एम राइटिंग दिस इज माय फंक्शन ft, राइट? So what I'm doing with it, I'm just substituting the upper limit here, which is gx, and differentiating it, and then I just substitute the lower limit here and differentiate the lower limit. That means we can also write it as f of upper limit UPT represent the upper limit, UPL actually represent the upper limit. So let me write here. So this is like UPL, and then we have to differentiate the upper limit, and then we have minus sign, and then substitute the lower limit LPL, lower actually LWL. I hope you can connect with this short and abbreviation, whatever it is. So LWL is like lower limit, and then we differentiate the lower limit. So what I'm doing here, this is our basic idea, right? This is the basic idea what I'm doing here. If I am differentiating a function, uh, differentiating a function, no, differentiating an antiderivative. So we get as a form of product, we get like first substitute the upper okay. So first substitute the upper limit, and then differentiate the upper limit, and then and then substitute the lower limit, and differentiate the lower limit. So this is our basic idea. Okay. So how we gonna implement? So we are implementing through this basic idea. Don't remember this formula, because this formula वो practice करते करते चीजें खुद ही जहन में आ जाएंगी. So you have to just go through this basic idea. We have to uh, substitute the upper limit, and then differentiate the upper limit with respect to x, and then substitute the lower limit, and then differentiate the lower limit. So let me prove it first. So okay, let's start its proof. So our proof something look like proof. So what I'm doing here, uh, our integration is something ft dt from phi x to gx, right? And these phi x and gx are function of x. It's clear seen, right? Like ये दोनों जो function है वो x की function है, but in integration our elementary element is dt, right? So let me prove it. What I'm trying to do here. So first you have to let the function whatever it is ft dt. Let us suppose its integration will be like we already know that we are integrating this function with elementary element t. So whatever we get as an integral will be function of t as well. Okay, only t, not x. So what I'm trying to do here, let us suppose its integral will be some rt plus constant, right? So what I'm doing here, I'm using the concept of indefinite integration here. Like this is our given integrand, and this is our elementary element. So when we integrate this function, we get the integral as a form of as a function of same t or same elementary element, because our elementary element is dt. So we get the integral in function of t. So I hope you'll all understand this what I'm trying to say. So let us suppose when we integrate the function ft with respect to dt, we get an integral rt plus some constant, r is a function of t plus some constant. Now what I have to do, when we differentiate this, okay, when we differentiate this, so actually we learn in indefinite integration, basically integration is nothing but the reverse process of differentiation. Reverse process of differentiation. We already deal with this thing in our lecture number 1 of indefinite integration. So what I'm trying to say here, if I differentiate this function, we get the integrand. Like I'm trying to say, if we differentiate the integral, we get the integrand. And if we integrate the integrand, we get the integral, because integration and differentiation are reverse process of each other. So what I'm trying to say is if I differentiate this is our integral, right? So if we differentiate this, what I get, let me differentiate it. So we get r dash t. I mean differentiation of function r with respect to t, we get a function ft. What I'm using here, I'm just trying to do differentiating the integral, we get integrand. This is the lecture number 1 indefinite integration thing that I'm using here. We get the integrand, and our integrand is nothing but f of t. Okay. So let me now let me call this whole integration, which is something as y. So what I'm trying to do here is our y is nothing but f of x, phi of x. Our lower limit is phi of x, upper limit is g of x, and our function is look like ft dt. Okay, so we know that the integration of from equation 1, we know that the integration of function uh, with respect to elementary element dt is rt plus some constant. So let me rewrite here. So r as a function of t and inserting the limit in it. So when we insert the limit, what we get? We get r as a function of gx and minus r as a function of phi x. So what I'm trying to do here, I just substitute the limit here, upper limit and lower limit. I hope you'll all understand this, what I'm trying to do. Okay. So I'm just substituting the limit here, phi x and gx here now. Now what I have to do, our y is something look like r of gx minus r of phi of x, right? We can say this now. And it is also equal to something like phi x to gx ftdt, right? From there I got this result, right? So we can we actually write this and this in one line. I'm doing nothing. I just write the y term and this term and this term in one line. Now try to differentiate the both concept. Like if I do dy by dx here, because finally we have to get in the form like d by dx integration of from phi x to gx ftdt, right? So we actually get this term, and now I have to just create the d by dx term. So what I have to do? Differentiate it. So let's differentiate it here. So what we get here, when we differentiate it, so we get actually r dash of g of x, and then using the chain rule, actually let me write here, using chain rule of differentiation. I hope you'll already know this and you learned this thing in your differentiation chapter as well. So do like g dash of x minus r dash of phi x, phi dash of x, right? And is equal to d by dx integration from phi x to gx ft dt, right? So let me erase it here. Okay. So I hope you'll all understand this, what I'm trying to do here. I'm just using the chain rule. So now we actually know that using the indefinite integration first lecture thing, differentiation of integrand is integral is integrand. So we are differentiating the integral. R of t is our integral. Let me rewrite here. This is our integral, right? So we can write this as r dash of gx. We can write it as f of gx g dash x minus f of phi x phi dash x is equal to d by dx phi x to gx ft dt. And this is our favorable form that we have to prove. This is the Newton-Leibniz formula, which is proved. I hope you'll all understand this. If not, then let me recall it again, right? Right. What I'm doing here, and हमने क्या क्या करा है? Let me recall you. Okay. So this is actually the Newton-Leibniz formula look like. So I will give you first the basic idea. So how to approach the and implement this formula. So there is our function given. So what I have to do, I have to insert the upper limit in it and then differentiate the upper limit minus insert the lower limit in it and then differentiate the lower limit. This is differentiation sign. Okay. Now we are moving to its proof part. So we have to take some idea जो हमने पहले पढ़ रखी हैं indefinite integration part में. तो वो basic idea यही था कि differentiation and integration both are reverse process of each other. Right? Now, what I'm trying to say here is, and what I'm trying to use it here is also important. So what I'm assuming, if we are integrating our integrand, which is a function of t, with respect to elementary element dt, we get a function r is a function of t. बेसिकली अगर मैं एफ टी को इंटीग्रेट करता हूं तो मुझे कुछ एक फंक्शन मिलता है आर इज अ फंक्शन ऑफ टी. ओके, आर फंक्शन है जो कि टी का ही फंक्शन है. देन if we differentiate this integral, we get the our integral, right? Now what I'm doing here, I am doing the definite part, like means we are inserting the limits in our function. So when I insert the limit in it or substitute the limit in it, what I get, r of gx minus r of y, just inserting the upper and lower limit as according to the given in question. And then what I do, I generate each and every single thing just misses a dy dx term. So I just differentiate the whole term. And in last step, what I'm using here to here, I'm just using the one thing, which is actually the differentiation of integral is integrand. So when we differentiate the integral, we get the integrand, right? So we prove the Newton-Leibniz formula. Actually, it is important. So now let's move on to its implementation part. So let me show you by examples, like how to implement this. So I'm again telling you, we have to use the basic idea of this. We have to insert the upper limit, differentiate the upper limit, minus sign, inserting the lower limit and differentiating the lower limit. So we have to use this concept. So let's start to our problem section to learn how to implement this. Okay, so our example first. It's something look like d by dx, and we are integrating it from x squared to, okay, let me erase it from here. It makes something different sense. Okay, x to x cube and sine of t dt, right? So we have to find its value. So what I'm telling you, you have to do nothing. Its value is directly is equal to, when we are using first, you देखो पहले तुम्हें फॉर्मूला पता नहीं है तो ट्राई टू राइट द फॉर्मूला है एंड देन ट्राई टू डू हमें करनी क्या है. सो वी नो दैट यहाँ लिख देना यूजिंग न्यूटन लेबनिज फॉर्मूला, NLF. NLF actually short form abbreviation, which means Newton Leibniz formula. Okay, so we can tell in short form like we are using NLF. Okay, Newton Leibniz formula. It's actually shorthand notation or abbreviation, whatever you want to say, you can call it. So d by dx of f of t dt from phi x to gx is nothing but f of g of x. We are inserting the upper limit, differentiating the upper limit, minus inserting the lower limit and differentiating the lower limit. So the same thing we are gonna do here. So we have to find like d by dx of x squared to x cube sine of t dt. So what I'm doing here, I'm just doing, we are inserting the upper limit here, sine of x cube, differentiating the upper limit. So we know the differentiation of x cube, it is 3x square minus sine of inserting the lower limit here, x square, and now differentiating the lower limit. So it is 2x, right? So this is our final solution. It is as easy as bread and butter, right? We have nothing to do just to apply this formula. And what I'm doing here, I'm just substituting the, inserting the upper limit, differentiating the upper limit, inserting the lower limit and differentiating the लोअर लिमिट इट इज वेरी इजी। जो भी हमने अभी तक प्रॉपर्टी इंप्लीमेंटेशन वगैरह पढ़ा है उसमें सबसे इजी इसी की इंप्लीमेंटेशन, बिकॉज इट्स लाइक ब्रेड एंड बटर। इसमें कुछ करना ही नहीं है, जस्ट टू insert the upper limit, differentiating the upper limit, inserting the lower limit, differentiating the lower limit. That's it. Game over. Okay. But you have to learn something new thing in it, and it also has complicated problem. So उस पे भी अपन deal करेंगे. First learn to how to implement the NLF. So this is the prior thing that we have to learn here. Okay. So let's raise the level of the question. Okay. So our second question is something look like, let me rewrite here. Our something x is equal to 0 to y, right? And dt by root under 1 plus 4 t square. If d square y by dx square value is equal to ky, then find the value of k. This you have to find, right? So, okay. So how to approach this problem is one thing. So actually, what question is saying, like, give me a moment. Okay, sorry for some wait. Okay, so let's move on to the problem. So what is problem is here? So we have to integrate this function, whatever we have to do, but we have to do something like to create the d square by dx square term. That means we have to differentiate here and differentiate the what? Differentiate the integrals here, right? So what I'm doing here is differentiate LHS and RHS with respect to y. I'm trying to say it's like do dx by dy. Although we have to calculate the d square by dx square, but uh, how to do here? Because y is not independent. Y is implicit function. Na? It is not explicitly connected with x. We can connect it in further more step by doing some calculation, but right now it is not actually directly connected to uh, x. So what I'm doing here is, let me do it here. We are doing dx by dy. So let's start doing dx by dy. So how we get and how to do, let me write here. Okay, so let's do dx by dy. Okay, so when we do dx by dy here, and d by dy integration of from 0 to y, dt by root under 1 plus 4 t square. Okay, so I hope you getting me what I'm doing here. Okay, so now this form is perfectly suitable to apply the NLF. So let's apply NLF here. So what we get? We get dx by dy is equal to, when we are applying NLF here. So I hope you directly can do. Otherwise, let me write here d by dx. Here we can change any function, whatever differentiating there is the function of that. Okay, so we are applying here dy by dy. Okay, let me write here clearly so you can understand. There is the function like d by dy we are doing here. There is the function like y function, g of function of y, and ft dt. So it is also equal to, we are inserting the upper limit here, differentiating the upper limit, minus inserting the lower limit here, and differentiating the lower limit. So do the same thing here. Whatever I do here, just do the same thing here. So what we are getting, first insert the upper limit here, 1 plus 4t square, 4y square, 4y square, and then differentiate it with respect to y. So differentiation of y is nothing but 1 minus, there is 0. So we get the 0 thing. Okay. So now what we get from here, dx by dy is equal to 1 by root under 1 plus 4y square. So we also know that uh, you obviously read in your differentiation chapter like dx by dy is equal to 1 by dy by dx. So we can write it as like dy by dx is equal to root under 1 plus 4y square. Right. So we can write it into this term. Now what we have to do? We have to create like d square by dx squared. So we have to differentiate the function with respect to x here. Right. I hope you'll all understand this what I'm trying to say. We have to differentiate with respect to x here. So let's differentiate this function with respect to x. So what I'm doing here, d by dx of dy by dx is equal to d by dx of root under 1 plus 4y square. So obviously we have to use the chain rule first here because this is the function of y. So we have to first integrate with respect to y and then we have to differentiate with respect to x. So what we get from here, d square y by dx square is equal to, now differentiate it. So what we get, 1 by 2 root of 1 plus 4y square. Now differentiate it with respect to y again because y square term now. So it will be like 8y into dy by dx. I hope you'll all understand this what I'm trying to say. So here d square y by dx square is equal to, and what is the value of dy by dx? This is let's equation 2. So we can substitute the value of this is here. So there will be like 1 by root under 1 plus 4y square into 8y into dy by dx value is nothing but root under 1 plus 4y square. So this get cancelled to 4. So what we get? We actually get d square y by dx square is nothing but 4 into y. And what we have to find it here? We have to find like if d square y by dx square is something ky, so we have to find the value of k. So what is the value of k here? K is equal to 4. I hope you'll all understand this uh what I done here, right? This is a label of problem based on NLab. So you have to be attentive here. What I'm doing here is very much important. Okay, so what I'm doing here, I have to somehow I have to do this. I have to create this d square by y by dx square. So what I'm doing, I now in first case our y is not explicitly connected with the variable x. So we have to first differentiate with respect to y, and then we know, and then we're using this concept dx by dy is equal to 1 by dy by dx, and then we get dy by dx, and then we uh, again differentiate with respect to x. So we get the following as our answer. I hope you'll all understand this what I'm trying to say. So let's move on to the example number 3. You have to just learn how to implement and how to approach the problem, right? I'm actually teaching you each and every steps, like how to deal with it, how to uh, approach any kind of integrand which based on Leibniz NLF. So, okay. Now let's move on to the example number 3, which is actually look like it is easy. It is easy. So I hope you'll all solve this. So try to pause the video and solve, and then try to match the answer. So it is look like we are we are integrating a function from 0 to x, and it is actually equal to x cos pi x, where x is greater than 0, it is given. Then you have to find like f of 4. So it is easy problem. So try to solve it, or otherwise I am solving it. So try to pause the video and solve. and then try to match the solution. So let me solve it here. Look, we have to find the f of 4 and we are actually integrating the function f with something. So let's use NLF here. And I'm not writing the formula again because I hope you'll all uh, learn this by using several times. So let me use it directly. So be using the NLF, Newton-Leibniz formula. So it's something look like, but I'm saying it again, insert the upper limit and then differentiate it, and then insert the lower limit and then differentiate it. So we get the 0 and again differentiate on the right side. So what we get, cos of pi of x and plus x. Differentiation of cos is minus of sine, so minus sine of pi x, and then again with respect to so pi of x. Okay, so what we get it here, we get f of x is equal to cos of pi x minus pi x sine of pi x, right? And what we have to find it here, we have to find the value of fx at x is equal to 4. So do nothing. This is, let us suppose, equation number 1. So put x is equal to 4 in equation 1. So what we get, f of 4 is equal to nothing but cos of 4 pi minus 4 pi sine of 4 pi. So this term is 0 because the sine 2n pi is 0, right? But this term is actually 1. So we get f4 is value 1. I hope you'll all understand this, what I done here. It is easy problem, right? Yeah, it is actually easy. So, okay, let's move on to the next problem, which is actually based on extended form of Leibniz formula. This is important. This is it is also known as extended form of Leibniz. So we are gonna learning today extended. इसमें थोड़ी सी concept नई concept आएंगी. So you have to be careful here. Okay, so let me take the another example, which is based on, let me write here, problem based on extended form of NLF. Newton-Leibniz formula. I hope you understand this abbreviation as well. So let me write the problem. So our problem is something look like, we are actually doing a limit x tending to 0, 1 by x cube, and we are integrating from 0 to x t times of ln 1 plus t to the power 4 plus 4 dt. Okay, so this is given. You have to solve it. So I hope you'll all, let me tell you one thing before solving this question. I hope you'll all learn the L'Hopital rule in your limit chapter, right? So we are using the L'Hopital rule here, which is, if you don't recall right time, so let me recall it. जल्दी से recall करा देता हूँ मैं. So it is like if our limit of the form 0 by 0 or infinite by infinite. So if like x tending to 0, f of x by g of x. So if f of x, so this limit is of 0 by 0 form or infinite by infinite form. So what we do here, f dash by x and g dash by x, and then substituting the 0 term, right? So this is actually the L'Hopital rule. So we are actually using this in extended form of Leibniz problem. Okay, so I hope. Okay, good. So, so let's move on from RHS. from LHS, sorry, from LHS, what we get uh, applying L'Hopital rule, right? Before applying L'Hopital rule, okay, let me show you why L'Hopital rule is required here. So what I'm doing here is, uh, look, this is the term like we have to differentiate, right? So when we differentiate this term, because this is of the form like Leibniz, but when we apply the Leibniz, when we differentiate the antiderivative, when we take the derivative of antiderivative, so we have to differentiate it, right? Then we apply the, okay. So why we applying? So let me tell you why I applying here. So look at here, our integration is from 0 to x and x is tending to 0. That means this x is also tending to 0. That means our integral is tending to 0 and in denominator it is x cube. So it is also tending to 0. So what I'm getting here, our 0 by 0 form when limit x tending to 0. So we can apply L'Hopital rule, L'Hopital rule here. So let's apply the L'Hopital rule here. Applying L'Hopital rule here. So when we applying the L'Hopital rule here, what we get? We get limit x tending to 0. And we are actually using the Leibniz here. So what I'm doing here, substitute the upper limit first. So ln 1 plus x to the power 4 plus 4, and then differentiate it. So the differentiation of x is 1. And in denominator it, and in lower limit it's 0. So we get nothing into x cube. And then we have to differentiate the whatever it is in denominator. So it will be like 3x square. I hope you'll all understand this, what I'm trying to say. So when we again insert the limit x is equal to 0 here, so it's again of the form like 0 by 0. Right. So what you have to do, we have to again apply the what? We have to again apply the uh, L'Hopital rule here. So we can solve it easily. Or one more thing we can do is something like we use manipulation. So what manipulation I do here? Look at it. Limit of x tending to 0. First take 3 outside the limit. It is, we can write ln 1 plus x by x. Right? We can like first cancel it and then ln x plus ln 1 plus x by x, and then what we can write here, x to the power 4 plus 4. And we know that limit x tending to 0, ln of 1 plus x by x is equal to 1. I hope you learn this thing in your limit chapter. Okay, so this term is creating 1. That will be like 1 by 3, limit x tending to 0, 1 by x to the power 4 plus 4. Now insert the limit 0 here. So what do we get? 1 by 3 into 1 by 4. So our answer is 1 by 12. I hope we'll all understand this, what I'm done here. I just use the problem based on extended form of NLF, which is actually, we are using the concept of limit plus differentiation plus integration. This is the actual calculus. We are not using the concept of one chapter. We are using the concept of multiple chapter. We are using the concept of limit by using the L'Hopital rule. We are using the concept of integration by using the implementation of Leibniz formula, and we are using the differentiation concept by differentiating the numerator and denominator. Okay, so let's move on to the next problem.